Welcome back my dear friends, a very good morning, good afternoon, good evening to all of you wherever you are in this part of the globe. So, this is data analysis and decision making 3 course under NPTEL MOOC series, and as you know this total course contact hours is 30 hours, which when broken down into the number of lectures, considering each lecture is for half an hour, is there are 60 lectures, and the total spread of this total course would be for 12 weeks, considering we have 5 lectures in a week, and after each week we have the assignments, and that is in totality 12 assignments, and after the end of this course you will basically be taking the final examination. And my good name is Raghunandan Sengupta from the IME department at IIT Kanpur. So, if you remember, we are discussing about the concept of integer programming and how would you solve it. So, basically there were 2 methods. One was the Gomori cut method, where we basically had that constraint boundaries modified accordingly, such the corner points where you will basically find the solution would be only integers, and then one basically was the branch and bound method, where you basically start from the primary node and considering one of the decision variables x or x1, whatever it is basically a non-integer. You will basically partition into 2 distinct sets and then proceed in the direction by taking if you remember, the problem was basically P naught was the original problem. You broke down into P1 and P2 depending on the branching, and you will proceed in the direction where the optimum solution was increasing or decreasing depending on whether you are trying to basically maximize a problem or minimize a problem. And obviously, there would be degeneracy, inconsistency and so on and so forth. So, you will stop in those directions. So, if you remember the diagram, so there were many nodes which were basically colored in different colors, signifying that any improvement in the objective function, either maximization or minimization, would not be possible. So, hence we will basically not proceed in that direction. Once you find out one of the decision variables had been converted into integer, you will basically consider the next set of decision variables which are non-integer and proceed accordingly. So, obviously, the final result would be the best optimum solution for the linear programming concept, where you consider initially all the decision variables were continuous. Now, before we proceed into other areas, I thought that I will discuss two problems. The problems are not interesting. What is interesting is that how you formulate. The reason is that if you remember in the first 1 or 2 lectures, when we have started the concept of operation research and optimization, I did mention that obviously the techniques which you are going to learn are the solution techniques. So, solution techniques, so linear programming would be generally the concept of northwest corner method, Vogel's approximation method. Then you will consider later on the steeped descent method, steeped ascent method, depending on which way you are trying to handle the problem. There would be quadratic programming, there would be integer programming. There is the concept of Gomori cut, branch and bound, reliability method, robust optimization method. Obviously, we will consider the goal programming method, so on and so forth. So, the general techniques which you are going to learn are the solution method. But what was very important to understand is that once you are given a general scenario of a problem with all the details, our main task, if you remember, I said was basically to formulate the problem in the right manner, such that you are aware that what is the objective function, what are the constraints, what are the decision variables based on which you should proceed. So, I will basically today either in this class and also in the next class, which is the 41st and the 42nd class, I will discuss a general simple but interesting integer programming problem with all their details. So, here we start the first problem. So, this is the 41st lecture, as I mentioned, which is basically we are going to start the 9th week of the classes. Now, consider the scenario is like this. There are 6 cities, so and in a district. So, the district can be either in UP, can be in Andhra Pradesh, can be in West Bengal, can be any other state of India, and the district, it could have been like a city also with different municipalities and areas. So, but we will consider this as a district. The district must determine where to build the fire stations. So, obviously, when there is an emergency, the time taken for the fire engines to leave their stations and reach the area where there is an emergency, where the fire has broken out or some emergency has taken place, should be as fast as possible or as minimal. Obviously, you cannot make it 0, you will basically try to reach those places for the emergency as soon as possible. So, the district must determine where to build fire stations. It also knows the district authorities knows or the district magistrate knows, or the superintendent of police or SSP knows, they want to build the minimum number of fire stations. So, obviously, the question is that why minimum, because in the minimum number of fire stations, if it is able to cater to all the needs, would obviously reduce your total cost, because trying to build up a building for the fire station, have people employed there, have different type of fire engines there, obviously entails cost, but the district authority wants to basically minimize that cost. And they would also ensure that at least one fire station is within 15 minutes driving distance. So, if you remember when I mentioned, they should reach the position or the place of emergency as fast as possible, considering the terrain of that region, the actual population of the district, and all the constraints or all the actual practical constraints which are feasible. The district administration thinks that any fire station should reach the emergency point within 15 minutes driving time of each of the cities. So, it can definitely be less than 15 minutes, but it should not exceed 15 minutes. The time in minutes required to drive between the cities in the district are shown in one table, which will come to that. So, they can definitely, the times can be 13.2 minutes, it can be definitely be 72.5 minutes, whatever it is, those values are possible. So, we will try to utilize integer programming. We will tell the district authorities, or basically help the district authorities how many fire stations should be built and where they should be located, such that these two important criteria which has been put forward by the district authorities are met. Number 1, the number of fire stations should be minimal, point 1, and point number 2, maximum time taken for any fire engine to reach the emergency point is basically 15 minutes or less. So, here is the general layout. So, on layout of the matrix, which basically gives you the time, if you remember, I had mentioned the time. So, along the first column we have city 1, city 2, city 3, 4, 5, 6. So, say for example, if I am I am giving a very hypothetical example. So, if it is in the district of say or this state of UP, you may consider. So, obviously, traveling from one city or to other city for the fire engines is not plausible, but I am just giving an example. It can be the city of Allahabad, Banaras, Kanpur, and so on and so forth. So, the cities are marked as city 1, 2, 3, 4, 5, 6 along the first column, and along the topmost row obviously you have also the cities. So, this is city 1, 2, 3, 4, 5 till 6. Now, as it is given, and we will another important thing, we will consider that city as points only, such that any movement within the city would basically take 0 number of minutes or 0 number of seconds, which actually practically is not plausible, but we will still consider for our sake as an assumption which is true. So, if you are traveling from city 1 to city 1, so obviously you will see the timing is 0. So, if I follow the concept that if you are traveling from city 2 to city 2, again time is 0, city 3 to city 3 time 0, 4 to 4 0, 5 to 5 0, 6 to 6 is 0, which means the principal diagonal is 0. That means, you do not take any time. If considering a fire station in that city, you would not take any time for the fire engine to reach that emergency area, point 1. Point number 2, we are considering the times. So, the times obviously are given. So, if you are considering that I am trying to travel, like it can be hours, minutes, whatever it is, but I am just writing the values. So, from city 1 to city 2 is 10, city 1 to city 3 is 20, city 1 to city 4 is 30, 1 to 5 is 30, and 1 to 6 is 20. Similarly, if I have the values, it is 2 to 1 is 10. Now, the important fact is that the time taken to traverse from point A to B or from point B to A is the same. That means, we have the same roads, same road condition, the direction of the traffic is such that there is no hindrance if it is travelling from A to B or B to A. It may be possible, say for example, during emergency, that if you are going from city 1 to city 2, you have to take route number 1, and if you are travelling from city 2 to city 1, you have to take route number 2. In that case, the distance travel, the time taken to travel would be different, but here we are not going to consider that, which means the matrix which you have for our consideration, considering the time frame or the time taken to travel between cities, is a symmetric matrix. The principal diagonal is 0 and all of the diagonal elements are equal. So, let us check 20 20, that means from 3 to 1 or 1 to 3. This is 6 to 2 or 2 to 6 is 10. Okay, yeah, here it is, there is some difference, right. I just missed it, sorry for that. So, here the timing given is, let me consider, this is 25, okay, this is same. So, this is 10 10, this is 20 20, this is 30 30, my mistake, it is same, it is a symmetric matrix, because it was placed in such a longitudinal manner, it was difficult to understand. So, you have 30 30, you have 20 20, that means travelling from 1 to 6, 6 to 1 is same, is 20. Then travelling from 6 to 2 is 10, and travelling from 2 to 6 is basically 10. Travelling from 4 to, say for example, 4 to 5 is 15, and travelling from 5 to 4 is 15. So, it is basically a symmetric matrix and all the times are given. So, they are basically in minutes and or seconds, whatever it is, and the values are given. Now, for each city, the district authorities must determine whether to build a fire station there or not. So, obviously, if a fire station is built, you invest money, you try to basically build up the building, employ people, if the city has to employ or the district administration or the authorities have to employ, and there would be fire engines in that particular city and the station, and if you do not, obviously, you do not invest any money. So, obviously, it is a yes or a no decision. So, let me continue reading it. For each city, the district authorities must determine whether to build a fire station there. We define that as 0 1 variable. So, if you remember, in the case of an integer programming, we said the values of the decision variables for integers, that means they can be 0 1 2 3 4 whatever. So, in this case they are 0 and 1, actually it is known as 0 1 programming, but we will consider that they are integers. So, it is absolutely possible to handle that in the realm of integer programming. Now, we define the variables which is 0 and 1 as x1, x2, x3, x4 and x5. So, as there are 6 cities, there are 6 decision variables. So, x1 is 1 if a fire station is built in the city 1, otherwise 0. Similarly, x2 is 1 if a fire station is built in city 2 or else 0. Similarly, x3 is 1 or 0, x4 is 1 or 0, x5 is 1 or 0, and finally, x6 is 1 and 0. So, in this case, say for example, there are fire station in all the cities. So, all the decision variables starting from x1 to x5 are all 1. Consider if, say for example, you have fire stations in only the odd cities, that means x1 or city 1, city 3, city 5. So, x1, x3 and x5 are 1, while x2, x4 and x6 will be 0. Then the total number of fire stations, in case you have they are being built. So, obviously, you will have the decision variables as x1 plus x2 plus x3 plus x4 plus x5 is and x6 is 0. So, hence the total number of fire station is sum of all them, which should be technically 6 in case if you are considering the 0 1 variable concept. Now, considering the matrix. So, we had already the matrix where the times were given. Now, I am considering that how many of them are within 15 minutes for each city. So, obviously, we will go in this direction. From city 1, the cities obviously 1 is within 15 minutes to itself. So, because the time taken to travel from city 1 to city 1 or 2 to 2 and within the jth city to the jth city were all 0. So, obviously, they would be included. So, city 1 to city 1 is included, hence 1 is there. Now, if you see the table, I will just go back to the table once. So, consider city 1, 1 is there, 3 will not be there, 4 will not be there, 5 will not be there, 6 will not be there, only city which is plausible from 1 is 2. So, obviously, in the set where you can reach from 1 is 1 and 2. Similarly, when I go to 2, as it is a symmetric matrix, 1 is also included, 2 is also included, 3 no, 4 no, 5 no, 6 yes. So, let us see for 2 it is 1, 2 and 6. So, we see as it is rightly we found out within 15 minutes you have basically city 1, 2, 6 from city 2. Similarly, when I go and consider from cities 3 perspective, 3 would be there, 4 is there. From cities 4 perspective, 4 is obviously there, 3 and 5 is also included. From cities 5 perspective, 5 is obviously there, 4 and 6, and finally, from city 6 you have basically 2, 5 and 6 included in that set. Set means that consideration set. Now, the district authorities must ensure that there is a fire station within 15 minutes of each city, that was one of the main assumptions. The table shown above, which we had just indicated, which locations can be reached to that particular city if you are basically starting from city 1. So, the only cities which can be reached is 1 and 2. So, let us see, if you have a fire station in city 1, it can cater to the needs of the emergency in city 1 plus city 2. If a fire station is in city 5, it can cater to the needs of 4, 5 obviously and 6. Similarly, if it is in city 6, it can cater to the needs of emergency for city 2, 5 and 6. So, the table shows that about indicates which locations can be reached from that particular city in 15 minutes or less. Now, we will basically bring in the constraints such that we try to basically minimize the number of such fire stations in totality. So, we will go from city 1 to 2 to 3, 4 and 5, 6, so on and so forth. It can be done in any direction, any order, but once we have basically included one city, it would not be considered in the next phase. I will come to that the point which I just mentioned. To ensure that at least one fire station is within 15 minutes of city 1, we basically add that constraint that for city 1, the constraint is x 1 plus x 2 is greater than 2. So, obviously, it would mean that there is one fire station within 15 minutes of city 1 and we are able to basically cater to that with that constraint. I will explain that in more details later on. This constraint which is I have just discussed ensures that if x 1 is 0 or x 2 is 0, it is not possible because 0 plus 0 cannot be greater than 1. So, at least one fire station has to be built which is within 15 minutes of city 1 because basically it caters to 1 and 2. Now, let us go to city 2. Okay. Now, you may be thinking why I am considering x 1 and x 2. Let us go back. So, if you see the first row, it basically means city 1 is only able to cater 1 and 2. So, obviously, x 1 plus x 2 is greater than 1 because either it is built in 1. So, obviously, 1 would basically be able to cater both the cities. Technically, if no fire station is built in 2, still 2 is basically catered by the fire station which is built in city 1. Now, consider the second constraint corresponding to the second constraint. It is given that 2 is able to cater to 1, 2 and 6, which means x 1 plus x 2 plus x 3 would basically have a constraint such that if only one of the fire station is built in city 2, it is able to cater 1, 2 definitely and 6 also. So, let us see that constraint. Similarly, the constraint corresponding to city 2 would be x 1 plus x 2 plus x 6 is greater than 1. It ensures that at least one fire station will be located within 15 minutes from city 2 such that is able to cater to 1, 2 and 6, those are the cities. In similar fashion, we can obtain the constraints for all the rest cities 3, 4, 5, 6, let us see. So, 3 would be x 3 plus x 4 is greater than 1. For the fourth city, it will be x 3 plus x 4 plus x 5 is greater than equal to 1. For the fifth city is x 4 plus x 5 plus x 6 is greater than equal to 1, and for the last city which is the sixth city, it will be x 2 plus x 5 plus x 6 is greater than equal to 1. Now, we need to combine. So, we will combine all these constraints. But what if you remember what I am sure we have not forgotten the objective. Objective was basically to ensure that z, which is equal to the summation of x1, x2, x3, x4 and x5 was minimum. That means, if only one, if it is possible that we have only one city which caters to all, if it was possible, then obviously that we would have basically minimized the cost. So, combining these 6 constraints with the objective function and with the factor that each variables must be 0 and 1. So, obviously, x1 can be 0 and 1, either a fire station built, not built. Similarly, for x2 or x3 or x4 or x5 and x6. Combining these 6 constraints with the objective function and with the fact that each variable must equal to 0 and 1, we obtain the 0 1 integer programming as follows. Now, so once I have mentioned that, let me basically state the objective function. We know we want to minimize z, which is the sum of x1 plus x2 plus x3 plus x4 plus x5 plus x6, such that constraints are corresponding to the fact that the minimum time taken to reach any one city from the other is 15 minutes. So, obviously, I will just mark this is corresponding to the first city, this is to the second city. First city was x1 plus x2 is greater than or equal to 1. Similarly, x1 plus x2 plus x6 is greater than or equal to 1 is for the second. This is the third, the fourth. Oh, this is too bold a marker. I will just remove it and then come to a pointed marker. So, this is the first city, this is the second city, this is the third city, this is the fourth, fifth and sixth. These are the constraints, and obviously xi where I is equal to 1 to 6 would be either 0 and 1. So, because either you build a station or do not build a station. Now, once you solve it, I am not going to the coming to the solution, because the solution methods have already been discussed concerning the Gombori cut algorithm and the branch and bound. Branch and bound I will come to that later, please have patience. So, once your optimum solution is solved, you find out that z is 2, and what are the solutions? You do not have any fire station in city 1, you do not have any fire stations in city 3 or city 5, only the fire stations are to be built is at city 2 and 4. So, hence x2 is equal to x4 is equal to 1, while x1, x3, x5 and x6 are 0. Thus, the district can build 2 fire stations, one in city 2 and one in city 4. Now, if I go back to the problem, say for example, now we make the constraint that a city has to be reached within 10 minutes. So, in that case, the set of cities which are minimum 10 minutes, it cannot exceed 10 minutes. So, in that case, the number of cities in case of city 1 would be city 1 and 2, obviously the same, because 15 and 10 will not make a difference. In case of city 2, now you will basically have 1, 2 and 10. In case of city 3, you will basically have only 3, because this 15 is now ruled out, because you have to reach that particular city within 10 minutes. For city 4, you have only city 4, city 5, you have only city 5, because these 15 are ruled out, and city 6, you have only city 2 and city 6. So, obviously, the constraints will change. In case if you are trying to basically build up that the fire station has to reach that particular city within 20 minutes and less, then again the constraint change. Constraint changing would be basically the first one will be if you have 20 or less, it will be x1 plus x2 plus x3 plus x6 is greater than or equal to 1, because 4 and 5 are ruled out. For city 2, the second constraint will be x1 plus x2 plus x6 is greater than or equal to 1. For the third city, it will be, as I mentioned, is 20 minutes. So, obviously, it will become x1 plus x3 plus x4 plus x6 is greater than or equal to 1. For fourth city, I am just repeating it, please bear with me. For the fourth city, it will be x3 plus x4 plus x5 is greater than or equal to 1. For the fifth city, it will be x2 plus x4 plus x5 plus x6 is greater than or equal to 1, and for the sixth city, it is basically x1 plus x2 plus x3 plus x5 plus x6 is greater than or equal to 1. Obviously, you will have the same objective function, sum of x1 till x6 is to be minimized, and then when you solve the problem you get a different answer. So, this is the only the constraint will change. So, do not worry about all these things. Okay. And coming back to this, these are greater than 1, obviously you will use the same techniques. I am sorry to repeat that, you will use the same techniques like add the slack and surplus, solve the linear programming, add the Gomery cards, or do the concept of branch and bound and then proceed accordingly. Let us consider a second hand example. Indian Auto is considering manufacturing 3 types of autos: compact, mid-size and large. The resource required for and the profits yielded by each type of car is shown in a table. I am going to come to that. Currently 6,000 tons of steel and 60,000 hours of labours are available, which is under the jurisdiction of Indian Auto. For production of a type of car to be economically feasible, at least 1000 type cars of that type must be produced. We need to basically formulate the problem as an IP maximization problem for the profit. So, the resources are given as this. So, the car types are given, there are 3 car types: compact, mid-size and large, like means the smaller car, mid value car and the larger cars. Profit yielded in rupees, I am considering, I am only reading the last row now. Profit yielded in rupees are given, even though those values are practically not very feasible, but still I will consider those values. It is 2000 for compact, 3000 mid-size and large are 4000. Labor costs are given for compact, mid-size and large are 30 hours, 25 hours and 40 hours, and the steel requirements are given as 1.5, 3 and 5 tons respectively for the compact, mid-size and large cars. So, the resource and the profit for the 3 cars are given. Now, because Indian Auto must determine how many cars for each type should be built, we define the following the variables. X1 is the number of compact is the variable, and obviously they would be integers, they cannot be continuous, like you cannot produce 2.57 cars or you cannot produce 100.792 cars. X2 is the number of mid-size cars produced, X3 is the number of large cars produced. Then hence the contribution you will basically have is basically, if you have 22,000 from the small, 3,000 from the middle and 4,000 from the big cars, the total maximization problem would be in thousands, will be 2,000 into x1 plus 3,000 into x2 plus 4,000 into x3. Now, we know that if a car of a given type is produced, then at least 1000 types are to be produced, and we will consider that x1 is cannot be less than. So, we should basically have that the number of cars produced has to be greater than or equal to minimum at least 1000, and the constraints, if we consider that steel and labor are limited. So, Indian Auto must satisfy the following constraints. For constraint 1 is either you produce or you do not produce. So, obviously, in that case x1 is greater than 1000, x2 is greater than 1000, x3 is greater than 1000. Constraint 4 is that car produced can use at most 6000 tons of steel totality, and the car produced must in totality use 60,000 number of man hours. So, with this I will stop 41st lecture and continue more discussion about the integer programming solution in the 42nd and lectures, so on and so forth. Have a nice day and thank you very much.